So I like this problem because there are a few things that, like, you've taken a lot of physics classes and whatever, and you've pretty much always had weightless cables and frictionless weightless pulleys. Well, in statics, when we did internal loads, we talked about how things change if the cable has weight. I think that's kind of cool to see for the first time. And then here's one where the pulley has a moment of inertia and it has mass, and we see how much that affects things. So practice problems on kinetics. Number 6. Okay, so you have this pulley that's connected to the ceiling, and it's holding up a 50 kilogram mass. And I guess it's not just holding it up. You're applying a known force of 600 newtons, and we want to see what kind of inertia, what kind of acceleration we have. So first, calculate the acceleration of the mass if the pulley is weightless. Does anyone want to see that one? That really, that's just set up for the second one so you can see how things change. But the second one, we're going to say the pulley has a mass of 3 kilograms and a radius of 0.1 meters. Okay, so, well, for the first one, I guess let's do it because it's fast. If the cable's weightless and the pulley is weightless and frictionless, then the tension is the same everywhere along the cable. So we can draw a free body diagram of the mass. We know that the cable tension is 600. And the downward force is 50 kilograms times 9.81, so 490.5. And so Newton's second law says 0,600 plus 0 negative 490.5 is equal to the mass times the acceleration, which we know is only going to be in the y direction. And so you get that 50A is equal to 109.5. And so A then would be equal to, what's that, 2.45? 2.19 meters per second squared. And that's going to be up, so the acceleration vector is 0, 2.19. So you did a lot of problems, and a lot of problems a lot harder than that in Physics 1. But it gets a lot more complicated when you add the mass to the pulley. So now the pulley has a moment of inertia. And so we're going to do 2 free body diagrams. For the mass, we have the weight, 490.5, And acting up, we have a tension that doesn't have to be the same as 600. I'll call that just T. And I guess we'll set that aside for now. Most of what we're going to be working on is the acceleration of the pulley. So the free body diagram for the pulley we have a force going this way of 600 and a force going this way of T. And we have a force in the middle. I'll call that FP. All right. Well, let's start by going through the rigid body problem for the pulley, and then hopefully whatever we need after that we'll be able to get from Newton's laws for the mass. So for the pulley, let's go through the steps. Step one, is there a fixed point, or do we have to do everything about the center of mass? It is the same in this one. There is a fixed point, though. So that's good news. That usually simplifies things. The moment of inertia is equal to the mass, 3 kilograms, over 2 times r squared. So that's 0.015, I think, kilogram meter squared. And we don't have to use the parallel axis theorem because the fixed point is at the center of mass. We already have the free body diagram. That was step 3. So that's this. Step 4, write out the table. I guess I'll put the coordinate system, put the origin here. Okay, so at the origin, the origin is at the center of the pulley, yeah. Okay, so there's a force, vector Fp acting at the origin. So Fpx, Fpy. The about point is the fixed point at the center of mass, so that's the origin. Subtract p minus a, that says the row vector is 0. And so take the moment and you get 0. All right, so now let's think about these two. Well, the direction of t we know, right? That's acting straight down, and so you might, reasonably assume that that's the last point that touches the pulley is at this horizontal position. The 600 we don't really know anything about. So how can we put this stuff in the table? Well, that's right, exactly. So so it turns out that without knowing what these force vectors are, like without knowing where they're leaving the pulley, we can figure out what the moments are because we know that they're tangent to the pulley at the point where they leave. And so that makes us sort of think like, okay, so what would we, by entering the moment that way, by calculating the moment, just knowing that it's going to be the force times the radius of the pulley, right? What information would we not have for the table? We wouldn't have the force information. So is that going to matter in this case? Why or why not? That's exactly right. Since we have a fixed point in this one, we weren't going to do Newton's second law anyways, or that wasn't in the set of steps. So we probably don't even have to deal with those forces as vectors, you know? So just having the magnitude and knowing that they're tangent to the pulley when they leave is enough for us.
How did you get the 3/2 of the dm?
This is the formula for the, the mass is 3. And the formula for a disk is 1/2 mr². Okay, so we don't know the point, any of this stuff. We don't know the force vector, but what's the moment produced by this tension force acting down about the center? .1 t, and then is it a positive or negative moment? Negative because it's making it rotate clockwise about the center. T. Yeah, the other one is going to be positive. Yep.
Could you really quick write down the Dell axis?
Yes. So the moment of inertia about some axis A is equal to the moment of inertia about a parallel axis going through the center of mass plus md². Right. I mean, as long as unless the fixed point is at the center of mass, which it is in this case. Yeah, right. Okay, so for the tension force acting down, we have a negative moment of 0.1 t. And then for the 600 Newton force, we don't know any of this stuff either. That one we could write as a vector, yeah. But we're sort of all the way committed to this approach because we don't know what to do otherwise for the 600. So I'm just going to leave it off. So the 600 Newton force is producing a counterclockwise moment, a positive moment of 0.1 times 600. So that's 60 newtons. And so now step 6 says Rn2L. We have negative 0.1 t plus 60 is equal to the moment of inertia, 0.015, times alpha, which we don't know. So negative 0.1 t minus 0.015 is equal to negative 60. That's our first equation. Yes, sorry. Okay. So how do we know that we're not done yet? Maybe we're done. Yeah, right, because we can't solve it. So we have to keep going. So now what are we going to do? So yeah, exactly. So now if we use the watermelon equation to calculate the relationship between the acceleration of this point and that alpha,
Acceleration of which one?
the acceleration of this point where that t is applied. We know that the acceleration of that point has to be the same as the acceleration of the mass. Okay? And so then we can use, with Newton's second law for the mass, we can come up with a constraint equation relating those two things, and we should be able to solve it, hopefully. Okay, so step 7. So watermelon equation for the point where the cable leaves the pulley on the right. Okay, so the acceleration of that point is equal to alpha cross r, so 0, 0, alpha, crossed with r. What's the r vector? 0.100. And we're given that at the instant we're looking at, the pulley's at rest, the whole system's at rest. So omega is 0. And so all of this centripetal acceleration is going to be equal to 0. Right? This all goes away. And so we get an acceleration of positive 0.1 alpha in the y direction. Okay. So now go to Newton's second law for the mass. Here's the free body diagram. So we have 0t plus 0, negative 490.5 is equal to the mass, 50, times the acceleration vector, which is the same as this one. So 0.1 alpha. Well, no, so if alpha is positive, then the pulley is angularly accelerating counterclockwise. And so that would make that point accelerate up. You know what I mean? If alpha is positive, it's going to accelerate this way, and that's going to lift the mass, and it's going to lift that point. Okay, so the second equation is t minus 5 alpha is equal to 490.5. And now we have two equations for two unknowns. I guess let's just do this by substitution. Who wants to do that? So two equations. Two unknowns. So t is equal to 5 alpha plus 490.5. So negative 0.1 times 5 alpha plus 490.5 minus 0.015 alpha is equal to negative 60. So negative 0.515 alpha minus 49.05 is equal to negative 60. So can someone calculate alpha? So 10.95 divided by 0.515. 1.26? Okay. Okay, yeah. 21.26 radians per second squared.
How did that change from A?
Because now we're looking at the mass. So the free body diagram for the mass is this. That 600 doesn't touch the mass anywhere. If this pulley was weightless, these two tensions would be the same and we wouldn't have to worry about it. But because that pulley is resisting, you know, these are different.
Not all that 600 gets.
Yeah, that's right, exactly, yep.
So now, will we just use that?
So now we can just, now let's plug that in and compare it to the acceleration. So the acceleration is 0.1 times alpha. So 2.13 radians per second squared, which I hope is smaller, you know. We'd expect it to be smaller, but maybe not drastically smaller than in the other case. And 2.19 compared to 2.13. It's kind of cool.
Did we do that in physics one before?
Oh, did you? I don't know. I mean, I guess everyone treats those topics differently. I had never seen that in any class, I don't think, before.
Now, can we do number 3?
Sure. Yes. 2 point, oh yes, meters per second squared, thanks. Are there any other practice problems you'd like to see?
Can we do number 3?
Yeah, sure. Oh God, yeah, that one. It's just so long. That's all. I'm just trying to figure out if, yeah. Okay, well, so kinetics. Number 3. All right, so you have an object like this with a rectangle removed. And it says the small rectangle has a length of 2 and a width of 0.6. And the big one has a length of 2.1 and a width of 1.3. And so I think my idea was that this, and this all have thicknesses of 0.05 meters. How would you come up with that? Just, then they're all the same, so that seems good. I don't know. I mean, so, and we have, okay, the long dimension, so this dimension is 40 degrees from the vertical, so we know this angle is 40. And at this point, we have a force vector of negative 200, negative 150. And at this point, we have a force vector of negative 400, positive 300. And did I include weight in this? Oh, neglect gravity. Okay. So those are the only forces. And then the angular velocity of this body is 0, 0, negative 6. And the velocity of the center of mass is 5, negative 3. And so the idea is that this door-shaped thing is flying through the air, spinning. When I was in 7th grade, the house that we had moved from in 5th grade, we hadn't been able to sell, so we were like renting it to people. And like while I was at school, the house next to it, I guess it had a gas leak, and it exploded. The house just like, and it totally bashed in the walls of the house that we owned and stuff. Like somehow nobody got hurt, but this one of those huge, heavy, like Minnesota front doors was like 100 yards across the street. Isn't that crazy? So that's what this problem's about, basically.
What's a small rectangle? Is that a window?
Yeah, that's a window. Yeah. Okay, so the objects, we have the density, 2,500 kilograms per cubic meter. And we have some information about the center of mass, and we know that this thing doesn't have any fixed points, so we're going to have to do everything about the center of mass anyways, so we need to figure out where that is. Okay. So to find the center of mass, well, here's how I would go about this, I think. Let's put the origin here. This angle is 40 degrees. That means this angle is 50 degrees. All of this, let's see. So to get this angle, you could think of like it's 50 to here and 90 to here. That means that this is 40. And it's 90 from here to here. This is 40, means this is 50. I don't know if you're following what I'm thinking here, if you care. But you do have to, you have to come up with all these angles somehow. And so this is going to be 40. And that's helpful because you can use that to figure out the coordinates of this point.
Which one?
The green one here. Okay, so the length of that side is 1.3. So the coordinates there are 1.3 times cosine of 40, 1.3 times sine of 40. Can someone calculate those?
0.996. 0.8.
Okay. And let's figure out the vector from here to here. So the coordinates of this point are going to be 2.1 times the cosine of, so the angle from the positive x-axis to get to this, the vector going from here to that green point, is 40 plus 50 plus another 40, so 130. So what do you get for those coordinates?
Negative 1.350, 1.60.
Okay. And now notice that, so 0.996 plus 0.836. Let's see. Let's name these. So this is A, this is B, this is C. And then let's call it D, E, F, G, going around the little rectangle.
How was the little rectangle?
So D here, E, F, G. So notice that .996, 0.836, those are the coordinates of C, but that also you can think of as a vector that has a length of 1.3 at 40 degrees counterclockwise from the positive x-axis. So we can get the coordinates of B by just adding that vector to this vector that we just got. So B is equal to negative 1.35, 1.609 plus 0.996, 0.836. Can someone add those? Yep. B is on the big rectangle. So I can okay, so I was going to use that to, so if we know all 4 of those points, we could average them, and that would give us the center of mass location of the big one. But actually, now that I'm thinking about it, we might just, if we just take the midpoint between A and C, that's probably the center of mass too. Well, we're going to come up with those 4 points and average those.
The intersection of D and F and E and G.
Yeah, right.
You don't know where it is, like you don't know where that rectangle is inside the big one. You just know how long.
Well, yeah. So I assumed that all of these thicknesses are 0.05. So whoever wrote this problem was just really easier to rotate the coordinate system. Yes, considerably. Yes. Did I do that in the...
Yeah.
Okay. Yes, that would be much easier. So to do that, if we rotate the coordinate system, then we just have to re-express those vectors. Okay, this is too much. Rotate the coordinate system. Okay, so now, how do we want to rotate the coordinate? If we want our new coordinate system to be like, let's say we want our new coordinate system to be this. What angle do we need? Well, okay, so positive 40 degrees for the coordinate system, because the coordinate system's going from an x-axis here and a y-axis here, counterclockwise to this. Okay, so theta is equal to positive 40 degrees. And so the rotation matrix is cosine of 40, sine of 40, negative sine of 40, cosine of 40. And so the force at A is that Q matrix times the vector negative 200, negative 150. Can someone who has that matrix on their calculator tell me what that is?
How did you get that Q matrix?
Just cosine of theta, sine of theta, negative sine of theta, cosine of theta. We did a bunch of this in statics. Okay. Okay. And then for B, it's Q times negative 400, positive 300. Okay. All right. Oh, 486. Okay. So now we can think of this problem, because all that matters mathematically is the relationship between the coordinate system and the object. We can think of this problem this way, where we have a force vector up here that is negative 249 and positive 13.65. And a force vector in the other corner that's negative 113.6, 486.9. Yeah, that's right. All right, so the centroid of the big rectangle is just going to be the midpoint of 1.3, 2.1, and the origin, so it's just this divided by 2, which is 0.65, 1.05. And the area of the big one is 2.1 times 1.3. What's that? 2.6 plus. And the centroid of the small rectangle is halfway between, so if the origin's over here, so this point is at, well, let's see, this one is at 2.0, and this one must be then at 1.4, so 1.7. Yeah, so I think the x centroid here is 1.7.
No, the bottom length, total length.
Of this. Yeah. So, oh, but okay, so this point, okay, so to get this point, you're at 1.3 minus 0.05. So 1.25. And then the other point, take away 0.6 from that, so you're at 0.65? Yeah, 0.65. So what's the average of 0.65 and 1.25? It's 1.55. No. What? 0.95. Okay, and then, oh, well, the y centroid is going to be in the same place as the other one. So that's going to be at 1.05. And the area of the small one is 0.6 times 1.2, was it? 2.0. So 1.2. So the total area is 3.93. The total area times the centroid is equal to 2.73 times 0.65, 1.05. Yes, I should have subtracted. I did that last class too. Okay, so what do you get if you subtract those? 1.53. No, we're going to finish this. No one's leaving till we finish this. This is like a 2-hour-long problem. And then 1.2 times 0.95, 1.05. Okay, so the centroid is equal to 2.73 over 1.53 times this minus 1.2 over 1.53 times the other one. Can anyone calculate that? Yep.
With the y really be the same for the small rectangle, but it isn't as long as the big one.
Yeah, but the top and bottom are both offset by 0.05. You know what I mean? So it's still centered in the same point. You know what I mean? I don't know. Well, we had almost gotten to the point where we could start doing dynamics on this. So that's a small victory.
It's 0.4147 and then 1.05.
Okay. So, well, let's think about the setup of this. So, is there a fixed point? No. So, we have to do it about the center of mass, and that's the location of the center of mass. So, the next step is calculate the moment of inertia. We'd have to do that by calculating the moment of inertia of the big rectangle, using parallel axis theorem to move it to this total centroid. Then calculate the moment of inertia of the small one, use parallel axis theorem for that, then add those two up. Subtract, yes. And then once we have that, we could start with the free body diagram and table and stuff. So sorry we didn't get very far in that. If anyone wants to do that one in office hours, I could keep working on it in office hours. But okay, that's it.